This is now we examine probability experiments where the outcome of a particular value of a quantity is, the outcome is a particular outcome of a quantitative variable. So basically the outcomes are always a number, and the number is always a quantity. Okay, and you'll see an example here. The variable is always denoted by an X, but sometimes, I said always, usually an X. It represents all possible outcomes for a random trial or an observation. The probability of observing a particular value of X is denoted P of X down here. Okay, any questions? Now, for a discrete random variable, this is one whose values are discrete. We talked about discrete values. They're ones that you can count. A variable whose values you can count or at least list in order. So discrete random variable, the values can be counted or listed because there are gaps between possible values. Yeah, so for example, the X could take on values of 0, 1, 2, 3, 4, 5, etc. Each of those values has a gap between 1 and the next. So between 1 and 2, there's no value that is possible for this variable because it's something you're counting. So if you're counting, the number of people, there's not going to be 1.5 people. So those are gaps between possible values. And then the probability distribution is where for each value of X, we associate a probability. Which will be P of X. Okay, and so you can see down below on the handout that there's a table where I'm going to have a bunch of different values for X, and then I'm going to figure out the probabilities for every outcome. There's a couple other columns that we'll fill in later, but we're just going to build a probability distribution. So the example, and again, probability distribution is where you associate to each value of the variable a probability. So when you toss 4 coins, we're going to let X represent the number of coins that land heads. Okay. Now remember, a sample space is just a list of all the outcomes. So let's see here. You could get 0 heads, so that would be 4 tails. Okay. You could get 1 head. That could be HTTT, or tail, head, head, tail, head, tail, tail, or tail, tail, head, tail, or tail, 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 head. So all of those are with 1 head. I'm going to kind of highlight those together. Okay. You could get 2 heads, so you could get HHET, or head, tail, head, tail, or head, tail, tail, head, or tail, head, tail, head. And all the different ways you can get 2 heads. Or tail, tail, oops, head, head, You guys, there's one more way to get 2 heads that I missed. Can you see it? Can somebody type it? I missed one of the ways to get 2 heads. Tail, head, tail. Thank you, Jason. Correct. Okay, so these guys all go together. I'm going to highlight them with a different color. Those all have 2 heads. Let's do 3 heads. So you could get the first 3 as heads and then a tail, or the tail could occur on any of these outcomes. So you could do head, head, tail, head, or head, tail, head, head, or the first could be the tail, tail, head, head, head. So that's with 3 heads. There are no other ways to get 3 heads. So I'll highlight those separately. And what's the last thing that I need to list here, just in terms of heads and tails? All heads. So the very last one is H, 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 like that. Yeah. Okay, so now my random variable X is the number of heads. Okay, so down in the table here, I want to list all the values for X. What's the first lowest value for X? Again, X is the number of heads. What's the lowest value for X? 0, correct. You could get 0, 1 head, 2, 3, or 4 heads. Okay. Now the probabilities. First of all, what's the total number of outcomes when you toss 4 coins? Each one of those outcomes up above is one of those total of the outcomes. What's the total number of outcomes? I don't mean individually. I mean the tail, 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 tail is one outcome. Yeah, there's 16 outcomes, Andrea. Thank you. Total outcomes are 16. So what's the probability of getting a 0 heads? One out of, remember probabilities, you have to divide. 1 divided by 16, I think, yeah. Good, so I'm gonna put in the probabilities. So there's only one way to get 0 heads out of 16. What's the probability of 1 head? Yeah, 4, but you gotta say 4 divided by 16, which is 1/4, correct? But I'm gonna leave it as 4/16. 2 heads, I think, is 6/16. Okay. 3 heads goes back down now, 4/16. And 4 heads, there's only one way to do it, so that's down to 1/16. Okay, I'm gonna pause for a second. Does anybody want me to explain this better? And when you list all the probabilities, you're describing how the probability is distributed among the outcomes. So again, that's a probability distribution. What do you think those probabilities add up to? Anybody? Yeah, 16 out of 16, which is 1. Oops. So the total is 16 out of 16, which is 1, and 1 is the same thing as 100%. Okay. So the question down below is, what's the sum of the probabilities? It says 16 out of 16, which is 1, or 100%. So that's why we sort of call this a probability distribution, because you're taking that total 100% probability and you're looking at all the outcomes and you're sort of distributing it amongst the outcomes. And in most cases, probabilities don't get distributed uniformly. They sort of have uneven probabilities. And you can see that here. The most probable outcome here is 2, which has a 6 out of 16 probability. Looks like we have to compute these on our calculator. So 1 divided by 16 is 0.0625. So I'm just going to put that in next to all this. 4 out of 16 is 0.25. 6 out of 16, I'm guessing, is 0.375. 4 out of 16 again, 0.25, and 1 out of 16 again, 0.0625. Okay, and we want to go ahead and graph these now. So all right, so I'm just going to do the heights of the bars. This is just going to be a histogram. So the first one's 0.0625, about that high. The next one's 0.25 right here. Next one's 0.375, gonna go right about there. Then going back down to 0.25. And back down to 0.0625. Just a little more than halfway up on that first line, like that. And then this is a histogram. Sorry about the noisy guys. That's our little bar graph. It says the bars should touch. Remember, histograms have touching bars, and there's a reason. I'm just going to give you guys a second to catch up. Coloring is sort of a great thing to do during pandemics. It sort of comforts you a little bit, so I like the color. The world is falling to pieces, but at least I have my colors. Anybody want to ask a question? No, 16 is the number of tosses. So I don't know if you guys see that question by Susan. When you think of outcomes, we're talking about the outcome. There's different ways of describing what the outcomes are, right? So right now, it was predetermined. I already knew I was going to toss 4 coins. The fact is that there are 16 outcomes. That's 16 arrangements of the 4 coins. Why wouldn't 16 represent the number of possible outcomes? It does. Okay, 16 is the number of possible outcomes. But when you say, what's and that's in the sample space. But right now, I defined X to be the number of heads. So the outcomes for heads are different for the outcomes for the number of heads is different for just asking, well, what are the possible tosses? So I guess it just sort of depends on what do you mean by outcomes. Right now, I'm looking at the outcomes for X, which was defined as the number of heads. Okay, and in that case, there's actually 5 outcomes. You could get a 0, 1, 2, 3, or a 4. Does that make sense? You're right. There are 16 individual arrangements when you drop 4 coins, but we're grouping some of them together. The one head happens in 4 ways. So that's an outcome, but it's not a simple event, it's a compound event. So I think, Susan, you're thinking of the simple events, which are the 16 things we listed up there. When I say one head, that's a compound event that we decided could happen in 4 ways. 2 heads also compound, so that happens in 6 ways out of 16. I don't want to sort of overthink this. I mean, we just listed that there were 16 outcomes up above here that I shaded in the different colors. And when I say, what's the probability of 2 heads, you just have to see how many of them had 2 H's and divide by the total number of outcomes, which was 16. Okay, and the only thing I'm really introducing is this weird variable X, which is counting how many heads there were. Okay, so I hope that helps. And don't worry about this too much, because right now it's just sort of in a theoretical realm, and in the end we're going to make this real practical. There's a question here about the total area of all the bars. So if you look at all these bars, they have a base, and I'm going to erase these notes, but the width of each bar is 1. And the height of the bar is the probability. Okay, so when you do the base times the height, that's just 1 times the probability. So the area of the bar is the probability of the corresponding event. So for 1 head, the probability is, what do we say up here? For 1 head, it's 0.25, but that's also the area of the bar. The area here is 0.25. The area is the probability. Okay, so the next bar has an area of 0.375. The next one's 0.25. The last one's 0.0625. That's the base times the height. And the height is the probability. Okay, the first bar is also 0.0625. So the question that's asked down here is, what's the total area of all the bars combined? Anybody want to take a stab at that? I'm gonna do a little cleanup on this. Pardon me real quick. Okay, so what's the total area? Anybody do it? Yeah, total area is 1. The total area is the sum of all the probabilities of X. Okay, so remember that's a Greek sigma. That means the sum of all the probabilities, which is 1. Okay, any questions about that? Now I think in your notes you have the formula for the mean from a frequency table, which is this one here. I think the only thing I would add is just, you know, we don't use that formula very much, but we can use that formula to convert it into a mean using probabilities. So if you just look at that formula, look what happens if you write it this way. This is the same result. If you wrote the f divided by the n like that, and then multiply by x, that's the same computation, just looks different. Okay, and when you think about f over n, that's just a relative frequency. Okay, a relative frequency is just the number of ways, number of times something happened divided by the total number of outcomes. So f over n, that was what we did with all of these up here. 1 out of 16, because there was only one way, that was the frequency, one way to do it out of a total of 16 outcomes. For one head, there were 4 out of 16 ways, so 4 ways to do it out of 16. Those are all relative frequencies, 4 ways divided by the total number of outcomes. So when I say f over n here, f over n is just p of x. So the mean for a probability distribution is just x times p of x. Okay, that's it. And so we'll be doing that computation in a sec. There's also a way to get a standard deviation from a probability distribution. You just kind of look at the graph. Whenever we see graphs like this, we're always saying, what's the center? Well, the center is the mean. And what's the spread? The spread would be the average distance from the mean, which is the standard deviation, which is just a measure of how wide that is. Any distribution of values has a mean and a standard deviation. And this is a distribution of probable values. We still want to know what the mean and the standard deviation is. So you can see the formula here for the mean, sorry, the standard deviation from a frequency table. And I'm just going to rework this a little bit this way. You've got this n in the denominator, so I think I'm going to write it as a 1 over n. You've got the sum of fx squared, and then minus a 1 over n also divided by another n becomes a 1 over n squared. Sum, oh, this is in parentheses, my bad. Sum of fx quantity squared, like that. And you could rewrite this way. The sum, you could, instead of having 1 over n, you can multiply that through with the distributive property and do f over n times x squared minus, watch what I do here, that n is being squared and the sum is being squared, so I can put it inside this way. I can do the sum of f over n x, and that quantity squared, like that. And then remembering that f over n is just p of x. That's just a probability. You can finish this up by saying, oh, well, that is just the sum of x squared times p of x minus, in parentheses, the sum of x times p of x, quantity squared. And then reminding you up above, the sum of x times p of x is the mean of the distribution. We use a mu for a population mean now. Okay, so that's the mean of the probability distribution. So I can say, oh, this is the sum, the square root of the sum x squared p of x minus the sum of x p of x, that's the mean up above, squared. So that's going to be the formula for the standard deviation of a probability distribution. And I've mentioned it in passing that variance is just the square of the standard deviation. So the variance of x is sigma squared. Now it's referring us back to the coin tossing experiment. It's asking for the mean and the standard deviation. So I'm just going to real quick remind you, the formulas are here. Okay? I guess I can copy them down here. The mean is going to be the sum of x times p of x, just from above, and the standard deviation, sum of x squared p of x minus the mean squared, and the variance is sigma squared. So we have to do these computations. But I'll tell you, when you do these by hand, anytime you see one of these sums in a formula, and there are two here, you want to add those up in a table somewhere. So that's why up above, I left two blank columns in the table. I've got an x column, a p of x column, but the mean needs a sum of x times p of x, so we need to add that up somewhere. And the standard deviation requires an x squared p of x that has to be added up as well. Okay, so you just multiply x times p of x. So on the first one, x times p of x is 0 times a 16th, which we'll just say is 0. Okay. Then 1 times 4/16 is, sorry, 1 times 4/16 is 4/16. Okay, then 2 times 6/16 is 12/16. 2 times 6 is 12. Okay. And then 3, oops, times 4/16, that's x times p of x, is 12/16 again. Okay, and then 4 times 1/16 is 4/16. Okay, so that's x times p of x. Looking to see if there's any questions about that. We've got to add them up. So 4 and 12 is 16, plus 12 is 28, plus 4 more is 32. So this thing adds up to 32/16. And I think 32 divided by 16 is 2. And I'm pausing to see if there's any questions. Okay, now the standard deviation requires that we do the sum of x squared times p of x. So that's the next column in the table. Just square the x and then multiply by the probability. So 0 squared is 0 times a 16th, 1/16 is still 0. 1 squared is 1 times 4/16 better be 4/16. So that's pretty easy. It gets a little more complicated now. 2 squared is 4, and 4 times 6/16. 4 times 6 is 24/16. Okay, now 3 squared is 9, and 9 times 4 is 36. That's 9 times 4/16 is 36/16. So these get kind of big. And then 4 squared is 16. And 16 times 1/16 is 16 times 1, 16 sixteenths. And then we need to add those up. And let's see, 4 and 24 is 28. 28 and 36 is 64. So 16, I think, is 80 divided by 16. Anybody want to take a stab and write down what 80 divided by 16 is? Yep, 5. Thanks, Susan. Okay, so let's just denote here, this first, the 2 was the sum of x times p of x. That was 2. And then the 5 was the sum of x squared times p of x. So again, that's 5. Somebody says, why 80? Oh, well, I just counted how many sixteenths I had in the last column, Johnny. So 4 and 24 is 28 plus 36, and that's where I did the math. 28 plus 36 is 64. And then there's another 16 80ths. Remember, when you add fractions, you just add the numerator. So I'm adding 4, oops, hang on. I'm adding 4 and 24 and 36 and 16 to get 80. And the denominators don't do anything when you add fractions. Johnny, you doing okay? Okay. Okay. So we've got our totals, and that's the hardest part about all of this, is getting these totals. Okay, so I'm gonna just bring that back down here. And this one and the other one. Okay, I guess I should have brought that down lower. Okay, so the sum of x times p of x is the mean. So the mean is 2. That is a lot of work to figure out something that's absolutely obvious. If somebody says, drop 4 coins, what's the average number of heads? 2. No kidding. So we can go back to the distribution up here. And in the center of the distribution, right where the mean should be, is mu, the center of the distribution. Okay, totally obvious, but this also works in cases where the numbers are messy and it's not obvious. And that's really what's more important here. Any questions? All right, next, the standard deviation. So we have to do the square root of the sum of x squared p of x. That's this guy over here I just circled. Okay, so x squared p of x, that's just a 5. Oops, just a 5. Minus the mean. Okay, the mean was 2. So it's 5 minus 4. That's easy. 5 minus 4 is 1. Square root of 1 is 1. So the standard deviation is 1. So the mean is 2, and the average distance from the mean is 1. Perfect. Variance is the standard deviation squared, so this will be 1 squared. So the variance is 1. Variance is important in the next section of the material. Okay. Let's see. Okay, I'm just waiting to see if anybody's got questions right now. Sorry, this is off topic. Go. I'm not sure that we're 1 week behind, but I am sure that I really can't do the test next week because right now attendance is optional, and it's not going to be required. So the test was supposed to be next week, but the campus is still, closed next week. So right now, I'm requiring that you at least watch these lectures, but it's just a homework thing. You don't have to attend the lectures, but the material is still required. I don't think I can test you next week. So I think we're going to push the test a week back. So what does that mean? I'm looking at my calendar real quick here. So the test is scheduled for the 27th. And I guess it's going to have to be April 3rd, right? Does that sound about right, you guys? Okay, we'll do April 3rd. But I'm just going to cover, probably cover whatever we get to next time. Okay, you guys okay? So we'll say April 3rd. Okay, Brian? No, I don't think we'll be taking it in class unless a miracle happens, and all of a sudden everybody's better in terms of the virus. So I think it's safe to say we're going to be doing an online test, and it'll be at 8:30 a.m. on Friday in 2 weeks. Okay, and I haven't figured out exactly. I think a bunch of it's going to be multiple choice because, chapter 1 was all definitions and stuff. Almost no computations in chapter 1. So I think it makes sense to do an online test that will be mostly multiple choice, and then you'll have some computations, and obviously that won't be multiple choice. What? Why sheesh? What's up, Andrea? Why sheesh? Oh my goodness. If you're gonna say sheesh, you have to say why. I won't be mad. Andrea. I see that, Brian. I'm waiting for Andrea. I think she could be unmuted. What if I unmute her? Andrea, why sheesh?
I don't know. Everything's so crazy.
That's all you got?
Yeah. I mean, I don't know. Like, we were open and then, like, kind of open, and now it's, like, completely shut down.
Yeah, I know. I think all the people in charge are just faking it right now. Is that safe to say?
Yeah.
All right, we're gonna, but I'm sure I'll have questions when I go back to do the homework. Will there be office hours? Yeah, I'm gonna go ahead and go back to office hours next week. Even though technically we'll be closed, what I'll do is, I think I'm gonna have you guys email me if you like me to meet during office hours. So I'll post this in Canvas. If you want to do a face-to-face office hour, we'll do it through Zoom or something like that. And probably Zoom's the best. But I'm not going to sit there waiting if nobody emails me next week. But I think the following week next week campus is closed, so they're not asking us to do stuff like this. But I'm going to go ahead and let you guys contact me if you want office hours. And then when you do, then I'll say, okay, will today's office hour be okay? And I'm just going to use the normal office hours that are in the syllabus. But if you need another time, then just let me know. Okay, I'm at home all the time right now, except for I'm giving some lectures now and then. So it'll be a lot more busy week after next. But next week is wide open. I'm only teaching 2 classes next week, and then the following week I'll be back up to 4 classes. Okay. Yeah, but I have no problem with this online thing. That's great. Good for you, Andrea. Brian's asking about a review session, and so I'm going to talk about that. You guys let me finish this lecture, and I'll show you where the review is. But again, it's going to be 2 weeks. There will absolutely be a review, and there is a review. It's already posted, as a matter of fact. I'll show you where that is, and I'll put it on Canvas. Okay, so going back to the next page, I just want to summarize what we've got here. So the first thing is that the probability of X is always between 0 and 1. This is just a summary of everything for this lesson. So I'll say for all X. The probability is between 0 and 1. The next thing we figured out is that the sum of the probabilities is 1. So that you have this that's your pie, and you slice it up, and the way you hand out the probabilities to the different events is how you're distributing the probabilities. It's a probability distribution. Then I think the next one was that the mean is also called expected value. Now it gets a new name. Okay. It's also denoted E of X. So these are all different ways of saying the mean. Okay. The mean is the expected value of the variable X. Okay. And then the formula is, as we've used already, it's the sum of X times P of X. Like that. And then the standard deviation is sigma. Okay. Sigma doesn't have a special notation. It's just the standard deviation. And so the formula is, as it was, sum of X squared P of X minus the mean squared, like that. So standard deviation. I'll make some more notes into this. So the mean expected value is also known as the mean. Okay. And then finally, sigma squared is variance. And you will see in the next lesson why this is important. Right now, it's just the square standard deviation. But we denote, it's so important it gets a weird notation, var x. The variance of the random variable x is how I would say that. Okay, and I was supposed to cover one more lesson, so that puts us one section. Somebody said we were a week behind. We're only one section behind if you look at the schedule. So today I was supposed to do, this was 5.1. Today I was also supposed to do 5.2. But we'll do that next Wednesday. Sorry, next Friday. Okay, so I'm going to turn the recording off.